Hello, I'm Pratik Kalshetti, a PhD student from Indian Institute of Technology, Bombay. I will present our Backview 2024 paper on Intrinsic Hand Avatar, a method to reconstruct an illumination-aware hand appearance and hand shape from monocular RGB video. This work is done in collaboration with my PhD advisor, Parag Chaudhuri. A user-specific digital hand model representing the user's hand shape and appearance is essential to realize a realistic and immersive experience in virtual reality and augmented reality applications. However, existing VR devices, including the Meta Quest 3 or the newly launched Apple Vision Pro headset, lack such a personalized photorealistic digital hand and thus fail to provide a sense of embodiment to the user. We tackle this problem of reconstructing a user-specific digital hand avatar from a monocular RGB video. We represent a hand avatar using a surface triangle mesh to capture the geometry and texture maps to capture the appearance. However, this problem has two major challenges. First, modeling the user-specific hand shape from just a monocular RGB video, and second, estimating high-fidelity hand appearance without baked-in illumination. Let's review previous work in this problem. For modeling hand shapes, implicit models were effective to approximate the geometry. In the case of sphere meshes, the radius and position of the spheres were adjusted such that the model was calibrated to the user's hand shape. However, there were too many parameters involved, and thus difficult to automatically optimize from image observations. Further, such implicit models could not leverage modern GPU hardware for efficient rendering, which is essential for real-time hand tracking applications. In contrast, data-driven mesh models, for example, the widely used Mano hand model, used blend shapes to offset a template hand mesh. However, the shape space is limited by trailing set, and these blend shapes cannot model high-fidelity geometry. Hand appearance capture has only recently received some attention. A naive approach is to register the mesh and copy the partial texture from the image observation. However, this produces texture spilling and blur due to slight registration misalignments. Another solution is to use a data-driven model of texture space. This regularizes the space for optimization, but this requires a high resolution scans of hand and it cannot capture hand appearances that are far away from the training set. More recent works have focused on reconstructing both the shape and appearance of hands. Neural fields, modeling occupancy and shading fields, combined with volumetric rendering, have demonstrated high-quality appearance reconstruction from multi-view and even monocular RGB videos. However, these methods do not produce consistent shadows on unseen poses, and further, they fail to generalize to unseen users or the same user under different lighting. To tackle the effects of lighting, the HARP method uses differentiable rendering without any neural networks for reconstructing the hand shape and appearance from monocular RGB video. It uses test time optimization to optimize the geometry and appearance simultaneously. However, it assumes a single light source and thus cannot handle general world scenarios where VR devices would be deployed. We propose a method to reconstruct an intrinsic hand avatar from a monocular RGB video. Our avatar representation consists of a mesh for geometry and texture maps for appearance. Our method uses test time optimization and thus can optimize to any new input using an analysis by synthesis approach. Our hand shape model can represent detailed geometry by using a coarse to fine subdivision while allowing per vertex offsets. Further, we use Disney's principal BRDF to produce photorealistic appearance. To disentangle illumination from appearance, we model the environment light using a HDR light probe. Finally, we utilize Monte Carlo path tracing to model self-shadows caused due to self-occlusion among fingers. Our avatar representation enables easy integration with existing graphics pipelines. I'll briefly walk through our idea. We start with a given frame and use an off-the-shelf 2D landmark estimation method to get 2D joint positions. We then use our initialization strategy to obtain the initial hand model parameters and the segmented image. Our hand model extends the parametric hand model mano by subdividing the mesh and the blend shape and also introducing vertex offset parameters to capture high frequency details. These initial hand model parameters are used to obtain the resulting deformed mesh. Next, we rasterize randomly initialized texture maps together with the mesh to obtain interpolated attributes at each pixel. Further, to model the environment light, we use a light probe which is represented as a 2D texture. We use this in a Monte Carlo based path tracing to obtain the shading image. Finally, we combine all this to get the rendered output. We then use L1 image loss between the rendered and input images to optimize the hand model parameters, texture parameters, and the light probe parameters. We also incorporate regularization terms to encourage smooth geometry and material texture. We optimize the hand shape, appearance, and lighting parameters using STD and Adam optimizers. Please read the paper for more details. Our image formation process is shown here. Our final rendered output is a combination of the diffuse reflectance, diffuse lighting, and the specular lighting. Here is the result of our final rendered avatar. Here is the decomposition result. And finally, here is the reconstructed avatar, showing the high fidelity mesh and detailed appearances captured in the diffuse reflectance and the normal map. We can now use our reconstructed avatar for various applications, for example, novel pose synthesis or relighting under different environment lights. We now compare our method with state-of-the-art multi-view hand avatar reconstruction method and observe that even with our monocular method, we can produce accurate self-shadows thanks to our ray tracing based shading. Further, our method produces a more detailed texture than existing monocular based hand reconstruction method. We also quantitatively evaluate our method against state-of-the-art hand reconstruction methods and observe that our method outperforms on all the metrics. We also compare our method with neural rendering based implicit models and observe that our method consistently performs better because of our physically based model. Here are additional results on our captured dataset. To conclude, we propose a method to reconstruct an intrinsic hand avatar from a monocular RGB video. Our reconstructed avatar is represented by a mesh and PBR material and thus can be easily integrated with standard graphics pipeline. Our key novelty is the disentanglement of intrinsic appearance from environment lighting, which we achieve by incorporating Monte Carlo path tracing in our end-to-end pipeline, leading to accurate self-shadows. However, our method requires a reasonably good initial pose and assumes static lighting throughout the video. Further, it cannot handle occlusion from other objects. This wraps up the overview of intrinsic hand avatar. Thank you for your attention.